Okay, so hopefully you found your notes from the last lesson. And on the last lesson, we mentioned how Newton and some others discovered what's called a derivative. Okay? And so I just want to remind you quickly what they did. All right? Okay, so the first thing is a function, f of x, is an expression, or it's an equation, right? Where if you input an x coordinate, it will automatically output a y coordinate. That's really a function's only job. You feed it x and it spits out y. That's all it does. Right? It does something to the x, you plug it in and it does something to your x. Out pops an answer. So you get x and your y coordinate is f of x. Okay? But there's more to graphing than just plotting points. For example, we said it might be interesting to just look at how steep that particular location is on the graph. If I had to describe this red point, I would say it's above the x-axis in the first quadrant. That's one way to describe it, but you could also say more things. Like you could say it's on a rising portion of our curve. That's a true statement that we never actually made, So maybe we need to start talking about that a little more. Yeah, it's in the first quadrant. Is it on a rising part of the graph or is it on a falling part of the graph? That's an important question. Well, it's clearly on a rising part of the graph. So what we want to do now is learn to describe the slope of this line. This is just called a tangent line. And it means roughly what it meant back in geometry days. Remember, here's a circle, draw a tangent line. Okay, Mr. whoever, or Miss whoever. Okay? It's just basically a line that brushes up against the curve and appears kind of parallel to the curve. So I think you know what a tangent line is. I don't want to spend a whole lesson on it. But we would like to describe the slope of that thing. And f prime of x has many names, but the input here is still the same x coordinate. And the output is now the slope. The slope of the tangent line. So the input is x, but now the function's job is different. The function's job is to spit out a slope for you, a new meaningful value that you can use. So I'll bet you if I plugged in x equals 2 into this function, it probably comes out to 2. That's probably 0.22, And I bet the slope is about 1. It looks like maybe it's 45-degree line there. Okay? But f and f prime are very independent of each other. Like they're not related. F gives you the y coordinate. F prime gives you the slope. Those are two separate ideas. All right. Any questions so far? Okay, so Newton and those guys, they had to figure out how they were going to get the slope of that line. After all, I thought slope had to have 2 points that you're comparing, right? So you can get a rise or run. So Newton and others came up with this. F prime of x is limo f of x plus h minus f of x all over h. And if you can't remember what that expression means, and you can't understand how they came up with that, you should look back at the first lesson, because that's what my whole point was last time. Okay, and please understand that this has many names. Some people call it f prime. Some people call it y prime. Some people call it dy dx. Some people call it d sub x, which I don't like, because it looks like Cramer's rule. Some people just call it the derivative. Some people call it the slope. And the verb they often use is take the derivative. Take the derivative, okay? Really means find the derivative, but take is the verb we use. Very strange. Take the derivative. Take it where? Supposed to take it to the park and push it on a swing or what? Take the derivative. It's like the phrase take a seat. It really means find a seat, right? Okay, so know that there's many names for it. And the two most common ones we use are this one here. This is called the Lagrange notation, named after Lagrange. Okay. And then there's this one, which is called the Leibniz notation, named after Leibniz. Neither of those were from Newton, but the ideas were. Okay, so we'll use the yellow ones primarily. I like the Leibniz notation because it just looks like slope. You know, delta y over delta x, except the delta is really small because you're actually only comparing one point to itself. Like the change in x is literally nothing. So dy dx is like a micro delta y or micro delta x, like a tiny little rise and run for 1 point. So we'll talk more about those later. I like the Lagrange notation because it reminds me that f was the name of the original function. I can't tell when I look at dy dx if the original function was called f or g or h or t. But from the Leibniz, or from the Lagrange notation, I can easily tell, oh, that was the function f, and I took the derivative. Here, I can see, oh, that's a slope. That's obviously a slope. If you want to mix these two notations, you can write df over dx if you want. Some people do that too. Forgot to write that one. Df over dx would be sort of a third and very common notation that I'll use. Okay? Okay, so enough of that. Let's try again a problem. So let's say f of x is rad x. Okay, now here's what people do when they are told to find the derivative. So I'll say take the derivative, or some teachers say derive. Take the derivative of. So you bust out the rule of the day. Okay, let's see here. F prime of x is supposed to be limo, let's see, f of x plus h minus f of x all over h. And they just kind of have this as a canned formula. Bust it out for the problem. Here we go. And clearly f of x is given. So you can just basically substitute this in right here. Right? Naturally. So you just go, all right, LIM, h goes to 0, there's an h on the bottom, there's a minus, here's my f of x. Right, there it is. And then people try to put in the f of x plus h. And here's where it all goes wrong. Because 90% of people, when they first do this, just write rad x plus h. But that is not what f of x plus h means. What does f of x plus h mean? X plus h is supposed to replace your x's in this function. So the radical covers both the x and the h, see? This is totally wrong. The bar goes over the h as well. And this happens all the time. And I'm hoping on this third or fourth time this year, you will stop doing it on my test and you will get it right. It's the square root of, not x, but x plus h. Okay. Unfortunately, to do a limit like this, we're supposed to plug in the 0. And that's not going to work out too good, is it? If I plug in 0 for h right now, I get rad x on top minus rad x, so 0 on top. And I get 0 on the bottom. That's if I plug in 0 right now. So I'm going to get 0 over 0. So I just put d and e, right? The limit doesn't exist, right? Is that right? No, we said if you get 0 on top and 0 on the bottom, you definitely don't put d and e. It might still be a meaningful problem. So what you need to do is use a conjugate or factoring or something. I'm not going to factor here. There's no x squareds or anything. So why don't we just multiply top and bottom by conjugate like we did on example 11 a minute ago. Okay? And hopefully we'll get to a point where we can plug in 0 for the h, you know. Okay, so let's do that. We're going to multiply top and bottom by root x plus h plus rad x. Remember, the top is a FOIL, although technically it's a full. There's no inner outer, remember? Who are you calling a fool? Okay, so the top, when you FOIL it, you just get root x plus h squared minus root x squared. The bottom is now the messier part of the fraction. Don't forget to park your limo out front. Okay, the top just becomes basically x plus h minus x. I'm having a deja vu here. I just did a problem like this a few minutes ago. The x cancels out by subtraction. The h cancels out by division, leaving us with limo 1 over garbage. But there's no factor of x on the bottom anymore. So now, or excuse me, there's no factor of h on the bottom anymore. So now we can plug in 0 for each of our remaining x's. So we're going to plug in a 0 for each x, and that gives us our final answer. 1 over rad x plus rad x. You don't need the limo parked out front anymore, do you? Because you just plugged in 0. Sorry, this should say 1 over rad x plus rad x. In other words, 1 over 2 rad x. Now listen, the student who put D and E on this problem, okay, the student who put D and E on this problem doesn't understand a thing. Let me tell you why. The function in this problem was rad x. You got to listen very closely to my logic here, okay? The function on this problem was rad x. We all know what the graph of rad x looks like. I had you memorize it earlier in the year. This is the function, right? The person who put does not exist was saying that there's no derivative. And when they said that, they were saying, listen to the foolishness, the folly of it all. There's no slopes anywhere on this graph. Really? No slopes anywhere on this graph. You kidding me? There's slopes all over that thing. Granted, there's one point, don't miss this, there's one point that I agree with you, there's no slope. At the origin. At the origin on this graph, we do have an interesting phenomenon. The direction is literally straight up. Remember I told you that the rad x graph is like a helicopter. When it first takes off the ground, it rises first and then it takes a direction. Remember that? I was referring to this lesson, okay? The slope is literally undefined when it first lifts off. There's no slope for a vertical line, remember? But for all the other points on here, they certainly have a positive slope, don't they? I mean, look at these other tangent lines that we could draw, you know. Over here at x equals, oops, that's an eraser. Over here at x equals 1, right? There's a slope right there. Over here at x equals 2, there's a slope right there. D and E? No. There's a slope. Maybe not at 0, but everywhere else there's a slope. Never forget what these problems mean, okay? If you make a statement like does not exist, that's a very bold claim. You're saying there's no slope. That can't be right. Please use your common sense when you're done with the problem, right? There's certainly a slope. In fact, I would rather you get stuck on this problem and then at the end write a note to me, say, hey, I know there's a slope at every point on this graph, except maybe 0, and of course the negative side, there's nothing over there. And make it an even more bold statement. Say a bolder statement. Say, hey, I think all the slopes are positive. See how they're all rising? At least show me something, okay? If you get stuck on the mechanics, show me some understanding. Write me a good note, okay? It might be worth something. Does that make sense? Okay, so yeah, there's a slope everywhere, just not at 0. And they're all positive slopes. Interesting. Okay, now notice, this is very important. Don't miss this. What was the domain of the original problem? What was the domain? All positives. What about 0? An expression like rad x. What can I plug into it? What am I allowed to plug in for x? That's what domain means, right? Any number that's positive, or 0, right? I can plug in 0. But look at the derivative now. Look at your derivative. What's the domain now? Can you plug in negatives? No. Can you plug in 0? Interesting. What does it mean for the domain to be positives only on the derivative function? It means that on the original graph, only the points to the right of the origin had slope. Okay? 0, but it doesn't have a slope. Okay. We'll talk more about that later. So the point x equals 0 is a very important point on this graph. It has a location, but it has no slope. The derivative told us that. The derivative told us that 0 didn't have a slope. Because you can't plug it in. Okay, now, the domain, write this sentence, the domain of the derivative is always a subset of the domain of the original. I'll say it again until it's written down by everybody. The domain of the derivative, write this, the domain of the derivative function is always a subset of the domain of the original function. Why? The domain of the derivative function is always a subset of the domain of the original function. Why? Because when you study a graph with many points and you ask which of these have slopes, you're naturally going to say all of them except these, or you know, all the points on the original graph except maybe x equals 0. That guy didn't have a slope. But it's impossible for this to be a superset of the original. If you put all real numbers here, listen, you're saying that every point has a slope. Well, there weren't even any points on the left. Like, are you saying those have slope? No. Your domain here needs to be a subset of the original. Now, a few nights ago, you did a worksheet, right? And I gave you a function that's a lot simpler than this one. You guys don't remember doing conjugates or anything, right? Yeah, it's a pretty simple problem. Everything kind of cleaned up. You started with a polynomial. What was the domain on that? Think back to your worksheet. What's the domain of a polynomial? You know, x squared plus 5. What's the domain? Anything, right. Plug in anything you want. The derivative was a polynomial. Right? What's the domain of the derivative? All real numbers again. So I'm not saying that the domain of the derivative has to be a smaller set. I'm saying it can be a proper or improper subset, but it is a subset nonetheless. This is going to be x is greater than or equal to 0, or x is greater than 0, or x is greater than 0, except these guys. Okay? But there's no way this could be all real numbers and the other one be only positives and 0. No. It doesn't make sense. So I get a lot of nonsense answers, and it comes from students who know mechanics, but when they make an error, they never catch it because they don't think about the meaning. They're just like, oh, I got all real numbers on this. Impossible. That's not a subset of x is greater than or equal to 0. See? So think about what everything means. And what is this guy's job? What is his job in life? He has one job in life. Give you slopes. So where do you guys want to find a slope? Pick any number. Make sure it's in the original domain, right? Don't pick -4. It's not even on the graph. 3? All right. So 3 is, of course, this point. It's basically the point 3 comma root 3. But the blue line there, that thing has slope 1 over 2 root 3. How do I know? Because that's what the derivative says. The derivative says the slope will be 1 over 2 root 3. Now I know a little bit more about this function. I know the slope at that point. And there's more things we could study, okay? We could actually take the derivative again. And what we get is the curvature. We could discuss how curvy the graph is near x equals 3. That's called the concavity and so forth. So I think we're done with this example, but I think it's super important. All the things I told you just now are statements you need to really, really understand. Let's go to our next example. F of x is sine x. Okay? Now I'm not going to be able to finish this example completely. So you're going to have to just watch the ending here because it is phenomenally profound. Okay? Before we do the derivative here, take the derivative. Before we do it, let's just see if we understand it. We have a sine wave. What's the domain? What's the domain? All real numbers. That's right. Do you think there might be a slope for each of these points? I think so. Okay, so I'm not going to put D and E. I don't care how gnarly the limit looks, I'm not putting D and E. I already know there's an answer to this problem. I believe every point on here has a slope. I don't even see any of those vertical cases, you know, where it's like straight up and down like on the rad curve. I don't see any of those. This is a real mellow curve. It's not like this is a semicircle, semicircle, semicircle. No, these are real mellow curves, and I think there's a slope everywhere. Okay? All right, so that's the first thing I'm going to decide. Now I'm going to write the rule. According to the definition of a derivative, the derivative is simply this. Well, it certainly looks harmless enough. Shouldn't this be real simple? Not so simple. The problem is getting that h to go away. How are we going to get that h to go away? All right, so I'll get you started here, and then you'll have to watch the rest of the video. The worksheet's not due till Monday anyway, so you can watch the rest of this later. But basically, the worksheet for this section, yeah, this derivatives 2 worksheet won't be due till Monday. So, but see this sine x plus h? A lot of people expand this the wrong way. That technically is sine x cos h plus cos x sine h. Okay? So that's just something people do. They misunderstand sine of x plus h. This is the identity we learned, remember? Okay, and then you might remember we actually talked about this limit back on our limits test. This is 1. I asked you to memorize it earlier in the year. It's just a fact. Everyone and their grandmother who takes calc has this one memorized. And the other one is this one, LIM h goes to 0, cos h minus 1 over h. This is 0. I think I had you memorize this one too. Can you guys remind me? Both of these are special limits. Everybody just memorizes them. They're actually a little bit hard to understand, but they will help us on this problem. I'm hunting now. I'm on the hunt for sine h over h. I see it right here. Trying to highlight that in blue. Does everyone see it? See the sine h over h? All right. Okay, so I'm going to kind of break this into 2 problems. Oh, you can't do those colors together. Evidently, you can't do those colors together. I'm going to break this into 2 problems. I'm going to break this into LIM h goes to 0, cos x sine h over h. That's this whole middle part. And a separate problem entirely, limit h goes to 0, everything else that's left over. Maybe I will finish this problem. So I kind of split it into 2 problems. I just grabbed that middle piece and just pulled it out and made its own problem because I recognized that little sine h over h guy. He looks familiar to me. Now, if h is changing to 0, I don't think cosine x really cares. So let's just pull him out. Changing h to 0 is not going to affect him. Let's get him out of the limit. And same thing with this sine x. Let's pull that out front. Okay, so now the problem looks a little simpler. See, it's just cos x has been pulled out, and we're doing limo sine h over h. And then here, sine x has been pulled out, and we're doing limo cos h minus 1 over h. And these are the 2 that we memorize. This is 1, and this is 0. These are the 2 blue ones I had up above I asked you to memorize. So the answer is cosine x. The derivative of sine is cosine. That's profound. The derivative of sine is cosine. What is this guy's job in life? What's his job? He's a slope calculator. for sine x is cosine x. Very interesting. So you'll be working on problems involving this. And actually the lesson there is complete. So you don't have to watch anything. But due Monday will be a worksheet, and I'll probably have you do the cosine version of this. I wonder if the derivative of cosine is sine, you know? We'll find out.